Hello everybody. Today we are going to start the last module of this course, and in this module we are going to touch upon couple of important points which are related to design automation, internal architecture of FPGA, how they are used, and also some of the pointers for advanced topics like how bigger designs could be designed, and what would be the utilities or what would be the future directions for this particular course. So in today's lecture we are going to focus on FPGA. So the question which we are going to address is what is FPGA, why it is used, and what is the internal architecture. What are the various design trade-off if we would like to design an FPGA? Okay, and also how configuration is done, how so basically about different trade-offs like fixed unit versus programmable units, fixed interconnection versus programmable interconnection. Okay, so the first question we would like to understand is what is FPGA. FPGA stands for a field programmable gate array. Field is usually an electric field, and programmable means this is a gate array which can be programmed using electric field or using electricity. So a gate array which could be programmed, or basically array of logic which can be programmed as any other logic, is field programmable gate array or FPGA. Now this was an early definition of FPGA, like the acronym FPGA is used when it was initially designed as a gate array, but slowly these gate arrays has become quite a sophisticated programmable circuits, but still we call them FPGA. In general, we can call these FPGAs are fine grain reconfigurable or fine grain programmable logic. So this is also in opposite to coarse grain programmable logic or coarse grain reconfigurable logic. So fine grain because each of the basic unit is very small, and it could be very small also with respect to number of logic it can implement, number of gates it can implement. So here most of the time the smallest unit which can be programmed is a 5 input gate or 4 input gate or a 3 input gate. Okay, and that's why it is called fine grain reconfigurable logic or fine grain programmable logic. Now since it is programmable, so it should have two components, programmable logic as well as programmable interconnects. So both of these things we have discussed in brief in one or more of the previous modules, but let's, for the sake of completeness, let's revise it here also to understand what is programmable logic and what is programmable interconnect. Here in this lecture we are using configurable logic block also as a replacement, or basically to mean the same thing as programmable logic. It's configurable logic block or CLB is being used as a programmable logic in this lecture. Okay, so what is a programmable logic? That we have seen earlier, that so before answering this programmable thing, let's also understand why these FPGAs are used. So FPGAs form one of the implementation method or implementation way of implementation to implement ASIC. What is ASIC? Application specific integrated circuit. Now we have certain applications. For example, in our last module, last couple of lectures, we have taken an application as a traffic light controller or a bubble sort or a GSG computer. So any of such application, or which could be algorithmic in nature or control based application. So these application we would like to implement a specific integrated circuit or one hardware for such an application. So if we would like to implement a specific hardware, application specific hardware for that particular application, we call it ASIC. Now let's say we would like to design an ASIC, then finally, we, as we discussed during the course that finally it will boil down to implement using gates, and gates would be implemented using transistors. So this standard procedure of implementing digital logic using gates and transistors could be quite a costly option if number of units we would like to manufacture is low, or we call it low volume also. Basically, number of units are less, then it could be quite costly. Why? Because generally this chip manufacturing or hardware manufacturing can be modeled as non-recurring cost plus. Non-recurring cost means a one-time cost, non-recurring cost plus number of units into recurring cost. So if number of number of units are less, or the volume is less, then this one-time cost, being a very high cost, could be this could make this particular chip or this particular hardware a very costly hardware. So to reduce the hardware cost, the number of units has to be increased. So you would ask this question now, that what we see these days, that every time a new hardware is there, new mobile phones are there, the cost is decreasing day by day. But here we are saying it looks counterintuitive that ASIC using transistors, or basically if we are designing a hardware, digital hardware, then it could be a costly affair. Since it would be costly only if the volumes are less, because this one-time cost, or designing the mask or setting up the design, that particular cost is very, very high, very large. So it runs into millions and hundreds of millions, or sometimes thousands of millions. But the factor which can reduce the overall cost is the number of units. If the number of units are also in hundred thousands or in million, then the cost of per transistor is very, very less, and it is reducing since years. So with every technology, the cost of transistor gets reduced, but the overall chip cost can be low only if the volume is less. So what if we have low volume and we still would like to have an ASIC solution? Then we can have Fpga as a cost-effective solution. So Fpga will be a cost-effective solution because it's a already manufactured chip, and we can use this chip to this chip is programmable, so that any ASIC can be configured on the same chip. So that is the most that's the value proposition for Fpga, that for it can be used to program any application, and because they are manufactured in large volume, so the cost of one Fpga chip could be much lesser than the cost of an ASIC. Okay, so now why there is still one more question, that why ASIC has to be designed and implemented. So usually the applications, like any algorithmic application, like you say sorting, searching, or we usually write a C program, and these C programs or high level language programs are run on a processor. Processor is also a hardware, so that means these applications can usually, if they can run on a processor, a hardware called processor, then what is the requirement of designing our own hardware for one particular application? So this itself is a big question to answer. So the reason we would like to have a specific hardware for one particular application is that application requires very high performance, because processor hardware is generic. So whenever any application would run on that generic hardware, then it would be slow in nature. So if we would like to have very high performance, or basically we would like to execute the same task in a very short time, then we would like to have application specific integrated circuit for these applications. So one popular example in these days is these machine learning applications. So the machine learning applications, if we try to run on laptop processor, even for a simple inference of a image, it may take a couple of seconds. Okay, so on the other hand, if we try to design a specific hardware for the same application, it could be done in a fraction of milliseconds. So that's why this particular thing would be required wherever high performance is required or some specific objective like low power is required. Then they're usually targeted, or we would like to design a ASIC for a particular application. Now so again we are saying that because if we would like to design an ASIC and these ASICs are in low volume, so the requirement is less, so then we can use FPGA as a cost effective solution. Now because of this particular requirement, FPGAs are also used for a prototyping solution. Prototyping means that we would like to first see whether our idea works or not. So whenever you would like to come up with a new hardware design, so rather than going for a direct transistor based design, many people would like to go for an FPGA solution so that they at least can prove to let's say funding agency that yes, this idea works, and that way, because the volume is less, so you would like to have only probably couple of units to show that this idea works. And then similarly, if you would like to launch a product which has which you would like to just see whether that particular product would be able to survive its purpose or not, then FPGAs could be used. Similarly, these FPGAs are also sometimes used as an emulation engine. Emulation engine means that you would like to you finally would like to design an ASIC, but FPGA can serve as a emulation engine so that we can quickly emulate that that final design, and then we can use this FPGA for debugging or for performance checks, etc. So these are the various use cases why FPGAs are used. So you will observe that for a simple logic, FPGA would require probably 8x to 10 times more area. It would be slower also, but because they could be cost effective solution, that is why FPGAs are predominantly used in industry. Primarily they are called as prototyping engine because they can serve as the requirement to prototype a particular design. Now after understanding why FPGA would be used, let's see that what is this programmable logic and programmable interconnect. So these things we have already discussed in previous lectures, so let's quickly glance through it. That we have seen that 2 is to power n input multiplexer can be used to design any logic gate with n plus 1 inputs. Okay, so for example, this is my 4:1 mux, and my input is A, B and C. So you can see that this particular design where 4 inputs, this is 0, this is 0, this is 0, and the third input is bounded to C. So this design essentially work as a you can see this particular design works as a 3 input AND gate. Okay, so similarly you can see that these inputs could be like 0 and 1, and sometime we can have this also as a third input. Okay, so but when we are trying to design this, we are trying to use these multiplexers as a programmable logic, then the combination which we use is that the input to all these multiplexer inputs are only 0 and 1. The input signals are not used in as an input to this mux. Okay, So if you would like to use this mux as a flip flop or a memory cell, then it would be difficult. So what is typically done, that we'll have a specific flip flop or a memory cell assigned to this. Okay, so finally, how this 0 and 1 would be given. So 2 is to power n into 1 memory can be used to give the n input to make this configurable. Okay, so this is also called lookup table. this memory of 2 to the power n into 1 is also called lookup table. Now the address to this memory is essentially the input to our logic. So let's say here the example which we have taken, A, B and C. So A and B would be the input, and the memory content 0001 etc. would be the content of the lookup table. So now the data of this memory is essentially the truth table of that particular function. Okay, so now because sometime we would like to have output which is flip flop based, another time we would require output which is non flip flop based. So typical architecture of programmable block is you will have an LUT, lookup table, and this LUT essentially means that we would, here the input to LUTs are 3, so that means internally there would be 8 into 1 memory. So there are 8 memory cells, and all these 8 memory cells are the lookup table, the truth table for these 3 variable function. And so with if we have this 8 into 1 memory, we can program this LUT as any combinational logic with 3 inputs. Okay, so there are 2 outputs to this programmable block, one as the unlatched output, the other one would be the latched output or output with a flip flop. Now because here this is given as a mux input, now there could be this could be used as a simple mux. If we gave another input D, so this D input can be used as a flip flop, or it could be this flip flop can take input from the output of the LUT. So this way we can this particular programmable logic can either implement any 3 input combinational logic, or it can implement one D flip flop, or it can implement both, one D flip flop as well as one 3 input non-latched output. So this way one simple programmable block could be implemented as a different type of logic. Now the second part is programmable interconnect. Now the programmable interconnect are usually divided. So this terminology is usually is borrowed from Xilinx, but other programmable devices, other programmable FPGAs will have a similar terminology. So here we are trying to in Xilinx they have 2 different type of interconnect. One is called connection box, another is called switch box. So the connection box are simpler one which takes which connects input output of CLBs to interconnect channels, while switch box connects vertical channels and horizontal channels. So how this thing will become programmable, how interconnect will become programmable, it with the help of switch box and connection box. And how do we say that this particular wire should be connected to the another wire? So for that there could be different implementation. One of the popular implementation, so one implementation is fused gates. So where you fused the wires, so that if that wire is fused, then it will get connected, one wire will get connected to the other wire. The other popular option is transmission gate. So transmission gates can be used for programmability of interconnect. So if the gate input of the transmission gate is 1, then the 2 wires will get connected. If the gate input is 0, these 2 wires will not get connected. So the gate would be connected to some memory cell, so that now using that memory cell, this transmission gate would be defining that which particular wire would be connecting to which another wire. So let's try to understand with a diagram. So let's say this the gray logic is a logic tile or a configuration logic block, and these blue squares are actually input and output ports. Now here we have taken a design where input output code could be on all the sides of my my logic tile or CLBs. Now you see there's a two requirement thing. So whether let's say to connect different wires, so there are some horizontal wires and there are some vertical wires. So if I would like to connect to my input output to these horizontal or vertical wires, I would still require a sort of a connection. So these blue ones are the connection boxes where input output is connected to either horizontal wire or vertical wire. So these crosses means that where this connection has to be made. So for example, this these input, whether we would like to connect to vertical channel 1, vertical channel 2 or vertical channel 3. So that would be our programmable interconnect. Now this particular connection is a simpler in nature. We are calling it connection box. So where input would be connected to some of the channels. Okay. So on the other hand, a switch box would be connecting more number of wires. There would be some horizontal wires, there would be some vertical wires. It would like to connect to these horizontal and as well as vertical wire. So the idea here is that this one of the input, let's say this input, should be able to connect to any of the 3 plus 3 plus 3, any of the 12 inputs. 9 inputs. This input should be able to connect to any of the 9 inputs. Similarly, all the inputs are able to connect to all other 9 inputs. Now one thing to notice here, that if we are using switch boxes, it doesn't matter whether input is connected to output or output is connected to input. So for example, this is the input connection and the red ones are the output connections. So this input connection can also be connected to the output connection or some of the other wires. So which means that when we use transmission gate, they essentially become wires. So the concept of direction is not there. So it's not that the voltage can only travel from this point to this point. So reverse is also true. If this is connected, so this can also give signal to this, and similarly basically your connection could be both ways. Okay, so this diagram has been taken from a tool called VPR, Versatile Place and Route. So this is a open source tool which has been designed to study or to explore how input output connections could be done in an FPGA. So a typical switch box is connected like this. For example, this wire could be connected to wire number 1 of this, wire number 1 of this. So similarly, all of the connections can be made. So all the possibilities are there that each wire can be connected to any other wire. Okay, so you can see the switch box could be quite sophisticated in nature, and there's some more trade-offs to this. So let's say this gives more bigger picture. Now here the number of channels are also quite large. So here 7 channels are there. 1 2 3 plus 3 7. So 7 horizontal channels are there, 7 vertical channels are there, and the switch box is connecting all these horizontal channels to vertical channels. Okay, so so more specifically here you see that rather than connecting all of them to all of them, it's connecting channel number 1 to channel number 1 here. Similarly the same thing we are seeing here also. Okay, so let's say we would like to connect some logic from one place to other place. So let's say this red connection is first connecting it to this, using the switch box it is connecting to one of the vertical wire, and this vertical wire is connecting using this switch box to one of the horizontal wire. And because this wire can also connect to this another vertical wire, so this way this output is going to input of this particular LUT or this particular logic tile or CLB, whatever we can call. So because of this configurable connections, any of the logic tile or CLB can connect to any other logic tile or CLB. Sometimes we will feel that the number of channels, number of wires which are required could be huge, or could be the number of channels required, or number of wires, number of input and output in connection switch boxes could be quite large. Okay, but that's the requirement for programmability. Now, if we would like to design our own FPGA, or whenever somebody would like to design an FPGA, there are various issues which he has to think over. The first thing he will, the first design question would be that how many number of inputs in LUT should be there. So should it be low in numbers? So for example, should it be 3 input LUT? 3 input LUT means that inside there would be 8 memory cells, and or it should be 4 input LUT or 5 input LUT. So you see, if the number of inputs in each LUT is less, let's say 3 or 4, so what we would require is, we would require large number of these LUTs. Okay, so but the issue or the difficult part is that any large circuit need to be decomposed into smaller circuits. So let's say if we have to design, we have only 4 input LUTs, and we would like to design 4:1 mux. So 4:1 mux would require 6 inputs. So then we would have to decompose this 6 inputs into a logic which would require all the 4 inputs. The number of LUTs required would be quite large, but the resources would be heavily utilized. So on the other hand, if the number of inputs are large, for example, let's say 6 input LUT or 7 input LUTs, what would happen in that case? Any function which require only 2 inputs or 3 inputs, most of the memory content would not be required. Many of the inputs will not be required, so that way it would be sheer wastage of hardware resources. Okay, so this is one thing. The other thing is that whenever we are designing using FPGA, or we see closely the implementation of these configurable logic blocks or logic tiles, then we see for implementing even a very simple gate like a AND gate or an OR gate, you require a complete logic tile or a complete configurable logic block. So this logic block, how can we improve the utilization? The improvement of utilization can be done if we can have some fixed logic. So rather than using a programmable logic, if we use some of the logic as a fixed logic, then it could be quite efficient. But then it loses its own objective that hardware has to be programmable. Still, to meet some performance goals, we would try to have at least some logic which is quite popular. So for example, if we are designing an ASIC and we try to see different application where this FPGA could be used, we see that addition is one circuit which is quite popular, which would be used in almost all the applications. So why not to design an fixed logic for some components which is quite popular or which would be used in most of the circuits. So so that means there could be some programmable part, there could be some fixed logic. What logic should be used as a fixed logic is always a question, or is a trade-off. Okay, so similarly for interconnections, the choices are even more difficult, even more varied. So for example, how logic blocks should be arranged, so whether they should be arranged in a 2D fashion or whether they should be arranged in a single line, how many logic block in each of the row or a column, okay, and how many wires should be there. So we in one of the previous slide we have talked about horizontal channels and vertical wires, horizontal wires and vertical wires. How many horizontal wires should be there, how many vertical wires should be there? That also determine what is the size of switch box or connection box we would like to have. So we see that some of the wires are local connections. So basically you would like to connect the output of one of the logic block to the input of the other logic block, while some of the connections are large fan out in nature, that one of the output would like to go to multiple of the inputs of different logic block, while some different kind of wires would be global in nature or semi-global in nature, where one of the circuit is going to all different kind of logic blocks. And sometime the connections between two blocks could be far. So basically the wire which you would like to connect from one particular unit to other unit, the other units are spaced quite far, some of the units are spaced quite near. So these are all different kind of issues, so which also give a question whether the wire should be distributed uniformly or non-uniformly. So or could it be possible that some of the wires could be long wires or some of the wires could be short wires, or all these connections, all these become the design questions, that how should we design these internal wires, interconnections. Now programmability is also an interesting question here. So whenever two wires get connected using a pass transistor, okay, or this pass logic, then it always slow down the wire. So basically whenever you are giving one and using a pass transistor logic, you are trying to pass this one to the other end, because this pass transistor internal structure of the pass transistor, it would the wire is much slower than the non-programmable wire or a direct wire. So that's why we will always think that if there are some connections which are more frequent, can we directly connect them, or can we make certain connection as non-programmable, or we provide that yes, these non-programmability would always give benefit in terms of latency or wire delays. Okay, so these programmability and choosing between which wire should be programmable, which wire should be non-programmable is a good question. Now some of the global logic, for example a clock and reset, has to be travel across all the logic blocks, so there may be some non-programmable wires for those purposes also. Okay, so how spatially input and output need to be organized. So in our previous, for example diagrams, we have seen that on all the four ends of logic tile or logic block, there were inputs and outputs. Should it be there all the way, or how they should be connected? These are all design questions for interconnection. Okay, so global signals we have already talked about, that there are some global signals where special wiring would be required, okay, which will usually be non-programmable in nature. Now after all these designs, then we can so that also gives us the clue that there would be different FPGAs for different kind of applications or different requirement. Based on the requirement, different interconnects could be designed. Based on the requirement, different kind of a logic block could be designed.